Alright, so let's do the second part of the lecture 4. Okay, so we're going to talk about acid-base neutralization reactions. Some of those acid and base that surrounds us is listed here. Vitamin C, for example, that's acid, by the way, and ammonia is a common base. Alright, so we actually talk about this two set of definitions for the acid and base. Arrhenius acid produce hydrogen, not hydrogen, sorry, H plus, and then the Arrhenius base produce OH minus, right? But that's not enough. We need a little bit more because some of those chemical is not defined by the Arrhenius acid and Arrhenius base. So we're going to have to talk about this Bronsted acid and Bronsted base as well. So the Bronsted acid is a proton donor. It gives off the proton. Proton is H plus. And then the Bronsted base is a proton acceptor. That's H plus acceptor. So it receives the H plus. So here's an example. I think I already talked about this one, but I'm going to repeat again. So NH3 is going to accept the proton, the H plus from here, right, to become NH4 plus. So that's accepted the proton, right? So that means that it's a base. This is a base right here. And H2O give off the hydrogen, right? Or the H plus. So that's going to be the acid. And if you notice that the reaction is going not only this way, but it's also coming back. So if I'm actually trying to look for the things coming back, then NH4 is going to give off H plus to OH minus to become NH3, right? So that one right there is acid because it's giving off the hydrogen, the H plus, right? And then OH minus is receiving the H plus. So that's going to be the base. And if I pair up, let me just try to clear these things. If I pair up these guys, that and that makes a conjugate acid base pair, and so does this one too. Alright, so that's good enough for these guys. The HF give off the hydrogen to H2O. So that one right there is acid. And then this one is receiving, so it's base, right? And then on the way back, H3O plus, by the way, the H3O plus is exactly the same as H plus. H plus doesn't really exist in the water. It actually exists as a form of H3O plus. So yeah, H plus, H3O plus, it's the same thing. So the H3O plus is going to give off hydrogen at the H plus to become water, right? So that one is acid, and then that one receiving, so it's base, right? Acid base pair, once again, it's going to be this and that, and then this and that. Alright, so let's do the next slide. The monoprotic acid give off the 1 protons, and then diprotic acid give off 2 protons. For example, like H2SO4. That one right there, if I simplify these guys, it's H2SO4 is gonna give off 2H plus plus SO4 2 minus. So it gives off 2H plus. So it's a diprotic acid. And there is a triprotic acid, and the diprotic, triprotic are called polyprotic, the bigger groups. And then you can do the same stuff for the monobasic bases too. The monobasic give off the 1 OH minus, and then dibasic give off the 2 OH minus. I have never heard of the tribasic base, but that's probably something that we can actually think about. Alright, let's do the acid-base neutralizations. That's the reaction that we are going to do. So acid is going to react with the base to produce salt and water. By the way, that if the acid and base is present in the solutions, it happens really often. I'm going to get into that one later. So the HCl, that's a strong acid, and the NaOH, the strong base, react to produce NaCl and H2O. So the water is the H2O, and then salt in this case is the NaCl. By the way, salt doesn't have to be the table salt. And if I write this reaction in a different way, you can actually write it in a sort of like a mimicking the solution, what's happening in the solutions. So HCl, as soon as you put it into the water, it becomes H plus and then the Cl minus, right? And then the NaOH, the same stuff, it's a strong base, so it's gonna separate into Na plus and OH minus, right? And then NaCl, by the way, it's a completely soluble solid, so it becomes Na plus and Cl minus. I'm gonna talk about this solubility stuff after the acid base stuff. And then H2O, that's just a liquid. So by the way, when you try to write this reaction stuff, always try to make sure that you write this AQ and the liquid and solid and gas. Please do that all the time. So this way of writing the equation is actually called ionic equations. So the previous one is called molecular equations. And if I'm gonna cancel these guys, because there are so many things that shows up on the left hand side and right hand side, Na2, those just gonna cancel. Then what we have is that H plus and OH minus in the reactant side, and then H2O is in the product side. And after the cancellations, ionic equations become net ionic equations. So the net ionic equation is really useful one. So every time we actually try to write out the molecular equations, somehow that you're going to have to write out the net ionic equations by going through these ionic equations and net ionic equations. So let's just try to do this particular equation, particular situation here. The solution of acetic acid and lithium hydroxide are mixed. Write the net ionic reactions. So I'm going to write out some actual formulas, because this one seems like it's missing the lithium here. I'm going to start out with the molecular formulas. Q, oops, plus, that's plus. Lithium OH is becoming C2, just cross that. Lithium C2, oops, H3O2, that's AQ, plus H2O liquid. So the way to do this one is if you see the very first letters as H, this only happens for the general chemistry, so don't count on this particular trick every single time. But usually in the acid-base reactions or the many of the solution chemistry stuff, the molecules tend to write it in this form. B minus. For example, like lithium OH. And you can actually see that this things becomes the lithium plus, and then this side becomes OH minus. So I can actually separate it here. So, and then this one right here is actually missing the lithium, right? So I'm gonna draw the line right here. And then all you have to do is to swap the partners here. So this and this is gonna combine together, and then that and that is gonna combine together. So what did I get? The lithium C2H3O2 and then H2O. So that is a molecular formula. And then for the ionic formula, I'm gonna put H plus C2H3. I'm gonna skip this black line. AQ. By the way, AQ is on the H plus too. I forgot to write that. Plus lithium plus. That's AQ too. Okay, I'm gonna skip that one. That's also AQ. The reason why I'm doing that is because I'm running out of the space right now. Lithium plus C2H3O2, that's AQ, minus plus H2O liquid. Okay, so that's the ionic formula. So that's ionic equations. Should say ionic. And then the net ionic is what we cancel the stuff on both sides, right? So the lithium shows up on both sides. And that guy right there is going to cancel, right? Then what do we have? We have H plus OH minus is becoming H2O liquid. And generally, many times you might actually find that the H plus and OH minus is becoming H2O. That may be the answer to the many of the net ionic equations, but don't count me on that one. But many times it happens to be that way for the acid-base reactions. Now what I want you to do is you can probably do these things by yourself. So I think this is good enough for this video, so I'm going to stop that.